Today we'll be looking at locking reads and comparing the differences between the select for update and select for share locking mechanisms that you can harness to gain different levels of locking strength for your queries. Both select for update and select for share fall under the category of read locks, and they're used in conjunction with select queries to express intent. What do you plan on doing with that data after you've selected it? For example, you might want to obtain the very latest data available in a table and then update that data, knowing that you've updated the very latest data available. Or you might just want to view the latest available data. These locks help CockroachDB order transactions, and when running CockroachDB in read committed isolation, they help bolster the strength of that isolation, avoiding any anomalies that you might otherwise encounter. So how do they both differ? Select for update obtains an exclusive lock for any affected rows. Only one transaction can hold an exclusive lock against a set of data, and only the holder of that lock can issue updates against those affected rows. So you're guaranteed to have the latest data, but also the ability to update that latest data. Select for share, on the other hand, obtains a shared lock against any affected rows. It blocks writes, ensuring that the holders of those locks have the very latest data, and it prevents any subsequent select for update exclusive locks against those affected rows. So you're guaranteed to be reading the most up-to-date data. Let's dive into the terminal and have a look at some examples of both. I'll start a local cluster. I'm running CockroachDB version 24.1. The default isolation level in CockroachDB is always serializable, but I'll enable read committed. I'll create a simple table to hold bank account balance information, and I'll insert two rows into it, A and B. Both have an account balance of 1000. I'll launch two new CockroachDB terminals, and now we'll perform some select for update queries. First, I'll open up a read committed transaction in the first terminal. I'm using transactions for this because if I was to perform the same thing outside of a transaction, the transaction would start and complete before it had a chance to observe the locking behavior. Now I'll issue a select for update, an exclusive lock against A, and I'll make an update. I'll increment the balance by 1. In terminal 2, I'll begin a transaction. I'll select everything from the account. This won't block because I'm not expressing any locking intent, and I'll see the original balances. The increment that I made in terminal 1 isn't visible yet because I'll only read what has been committed, and terminal 1 hasn't committed yet. I can create an exclusive lock against B because that's not affected by the original lock in terminal 1, but I can't obtain an exclusive lock against A because that's already held by terminal 1. If I commit the transaction in terminal 1, you'll see that that immediately unblocks terminal 2, and the latest value of 1001, the increment that we made, is now visible to terminal 2. Terminal 2 now has the exclusive lock for both A and B. If terminal 1 tries to obtain an exclusive lock against A now, it will block because terminal 2 has the lock for both A and B. Just to demonstrate, we also have the exclusive lock against B. If I make some updates in terminal 2, let's increment A by 10 and decrement B by 10 and commit. Terminal 1 is immediately unblocked and sees the latest decremented value of B. Let's move on to select for share. I'll revert the account table back to its original values, and I'll open up a transaction in terminal 1. I'll obtain a shared lock against A and begin a transaction in terminal 2. I can read the value for A in any of the terminals, and I can also obtain a shared lock from any one of those terminals. So terminals 1 and 2 now both hold a shared lock against row A. However, if I try to make an update, terminal 1 and 2 are currently guaranteed to be viewing the most up-to-date data for row A, so I can't make an update from any other terminal. That will block, while terminal 1 and 2 still have the most up-to-date data for row A. Let's commit those transactions, and this will allow terminal 3's transaction to run to completion. Because there are no more shared locks against that row, the update has gone through and the value has been updated. Now, I'm simulating long-running transactions here. Usually transactions will begin and commit or roll back very quickly. However, if you're operating in an environment with long-running transactions, you might not want to wait for those transactions to complete. There are a couple of mechanisms that you can harness to ensure that you're either skipping out early for any rows that you can't obtain a lock to, or simply failing if you encounter a row that's already locked. Let's have a look at both of those mechanisms now. I'll reset the balances again, and I'll begin a transaction that obtains an exclusive lock on row A. I'll begin a transaction in terminal 2, and you'll see that a simple select against the balance won't block because I'm not expressing any intent. But if I try to obtain an exclusive lock, that will block. We can use skip locked to return early and not wait for any locked rows. There is no balance returned because we encountered a locked row. But you'll see if I run another transaction that asks for both rows, the locked row and an unlocked row, and skip any locked rows, I can still return the balance of the unlocked rows. If I want to bail early, the no wait clause will return an error if I encounter any locked rows. And there's the error. Could not obtain lock on row A. Let's roll back our transactions, reset the balance one more time. Begin a transaction in terminal 1, and this time we'll look at what the skip and the no wait do with shared locks. Let's create a shared lock in terminal 1, open up a transaction in terminal 2, and try to obtain an exclusive lock on that shared locked row. We skipped because we weren't able to obtain the lock. We can obtain an exclusive lock on B because that's not currently locked. And like before, if we try to obtain an exclusive lock against A, which is blocked because of the shared lock in terminal 1, we'll receive an error. These locking mechanisms are important to use when running CockroachDB in Reid committed isolation. They allow CockroachDB to manage your transactions in a way that you don't encounter the anomalies that are present in Reid committed isolation. Depending on your requirements, consider using the select for update, the exclusive lock, and the select for share, the shared lock, when running in Reid committed to hint to CockroachDB as to what you intend to do with the data within a transaction.